let me just say a couple of words before I start. So ACTR actually represents yet another expertise that our group has, and which makes it even more unusual. Of course, no group in the world can have it all, but ACTR is one of the world experts in GRMHD, the author of one code that's state-of-the-art back, and it's really, again, a privilege to have you here with us. And it can add to the synergies, because on top of everything else, we can collaborate, do state-of-the-art astrophysics on the background of these solutions, that we can analyze the stability, we can see the lensing, and we can generate. So, effectively.
Thank you very much, Carlos, for the introduction and for the kind words. So indeed, I feel very privileged to be in this group. I have not been privileged enough to be since the beginning as Miguel or for a long time as Pedro, but I am very happy to be here now. And so my presentation will be focused more on my research line, on how it is now in the group and how it will be in the future. I'm not sure if this, yes, this. So, well, my research line, indeed, general relativistic magnetohydrodynamics and radiative transfer, is part of black hole astrophysics, or more generally, astrophysics in strong gravity environments. So this is driven by the question on how these objects, these marvelous solutions that are found in the group, or in general in theoretical physics, look like if they are placed in our universe. Because in the end, if black holes and exotic compact objects are real, they must interact with the familiar matter and radiation that is in our universe. So we can imagine ourselves as the experimenter that is here in his laboratory, and if some exotic objects, such as I saw this picture and think of these 3D renderings of the boson stars that are in many other papers. If some of these objects appears in the laboratory, how the researcher will know what he's seeing. So the history of black hole astrophysics is long. So here I have put some of the highlights. And of course, there is a lot that I have omitted. For example, I have omitted the history of gravitational waves, because this is a complete field on its own. But so we can see here that general relativity was proposed in 1915, or was completed in 1915. The paper was published later, but so it was already 110 years ago. The Schwarzschild solution came slightly after. And the solution by Kerr for rotating black holes came so long after that in the meantime between Schwarzschild and Kerr, there was the discovery of a radio signal from the galactic center by Karl Jansky. So this radio signal, later it was found that it comes from a very interesting source, that is Sagittarius A, and at the center of Sagittarius A, there is Sagittarius A star, the central black hole of our galaxy, of the Milky Way. So here you can see this source with a lot of more resolution than what was available in 1933. So here's the mini spiral that surrounds the central black hole, and from which matter is accreting into the central object. So later, shortly after the discovery of the Kerr solution, in 1964 there was the discovery of what was later known as the first black hole in a stellar mass binary. So that was Cygnus X1. During the next decade, there was a discussion on what the source could be. And in 1973, there was a very important paper by Novikov and Zorn, where they gathered a lot of information on what would be the astrophysics of black hole, and that made our mental image of how a black hole should look like, with this accretion disk that should emit in a very particular way, with some particular spectrum, and so on. Later, a few years later, there was a work that is very significant for what the EHT came to do later. That was the first simulated image of a black hole by Luminet. So here you can see that image. It was produced with the help of a computer and with that provided calculations, and then with hand filled ink. So, but here we can see some of the aspects that form already nowadays are standard image of a black hole with an accretion disk, a shadow, and this side brightened by the Doppler beam. So finally, well, many years later, it took many years for technology to allow us to actually have a real image of a black hole. And that happened, as Pedro mentioned in a previous presentation, in 2019. So this is the year where the first image of a black hole was published by the Event Horizon Telescope, and it corresponded to the black hole at the center of the M87 galaxy. So the Event Horizon Telescope is a full network of telescopes that spans over all the Earth, as you probably see and as you probably know. So it is a big organization that has more than 300 members, more than 60 institutions in 20 countries, and it currently has 2 members in Portugal. So one is myself, and there was recently another member that was hired this year at the EST in Lisbon. So after this famous image of M87 star, the collaboration imaged the first image the black hole at the center of our own galaxy. Well, actually, the data was acquired at the same time, but the image was harder to process and was published in 2022. Now, well, GRMFD simulations are essential to provide a theoretical interpretation for these images. And so here in Aveiro, the work that I have been most focused to do, and also in collaboration with some members here and in other parts of the MapFIS network, was focused mainly on 2 research lines. So the first research line is to figure out, to discover how flow patterns so what are the flow patterns in accretion onto low luminosity active galactic nuclei, such as precisely the HT targets M87 and Sagittarius A star. So this was done, or this is carried out indeed by general relativistic magnetohydrodynamic or GRMFD simulations, followed by radiative transfer calculations. And the goal of this research line is to improve modeling by going beyond typical simulation setups and including information from observation of the large-scale accretion flow. And here, well, you can see a picture of one of these simulations where one can see even at a larger scale, so the black hole is here is small, and one can see at larger scales the flow pattern forming organically. The other research line is indeed a synergy with the work that is carried out by many of the members of the GRAPH group, and is to try to investigate the observational appearance of black hole mimickers. Specifically, well, there are several extensions to GR and to the standard model that predict the existence of these compact objects that are able to mimic black holes. But specifically, the research has focused on bosonic stars, which are among the best well understood and best theoretically developed models. So here you can see a GRMFD simulation, a 3D rendering of one of these objects from work that is now in preparation in collaboration with Carlos and with our external collaborator Darío Núñez. Here, one of the most interesting results from the research of imaging bosonic stars was that an event horizon seems to not be needed in order to produce ring-like images as the one that was captured by the EHT. So, well, the question then is, how can we distinguish the 2 objects? well, and there are many questions that come out of this. Actually, this originated a whole research subtopic that had been pursued by the group. So this paper was out even before I came to the group, because, well, of course, I am not the only person working in this research line in the group. So the fact that it seems that really bosonic stars can mimic black holes, so that in the sense that they can produce shadow-like images, and that there is another mechanism to produce these images beyond, captured by an event horizon, has resulted in several questions that need investigation. So one of them is whether there are stable, long-lived bosonic stars that can mimic black holes. Another one is how robust are the processes that produce these ring-like images. And what is done in this research line in the Aveiro group is to seek an answer to these questions using GRMHD simulations. In addition to that, other work performed here in Aveiro was focused on looking at on understanding the astrophysical appearance of these objects in other contexts. So, for example, there was recently a paper that is now submitted but still in referee process on what would be the appearance of a boson star in a binary with a sun-like companion that was led by a PhD student from the University of Munich. So, what have we learned so far? So, regarding the first topic, we have found that there is a rich phenomenology that still needs to be studied in the patterns of wind accretion, and potentially this can help us learn more about the environment of black holes and to better interpret the results of DHT. We have also found that there are that there exists at least some stable objects that can meet sparkly shadows. So this is the paper in preparation from which I shown the simulation previously, and we have also studied that there are mechanisms that allow boson stars to mimic black holes, but that they tend to be very dependent on astrophysics, and this is also corresponds to another paper that is in preparation in the group. But, well, in addition to science, that is the main motivation that drives our work, I wanted to talk also a bit about what has been the activity of this research line in the group, and what are the outcomes that we have in terms of this activity. So I am speaking only from the time that I came here, so that was at the end of 2023. Up to essentially now. We are almost in December 2025. So, currently on this research line in the group, there have been 18 published papers, plus 5 more that are in preparation and that should be submitted or accepted soon. So, regarding this, there was a module that was offered as part of the lectures for the MAPTIS PhD program. This was exotic compact objects, theory and phenomenology. There are several student projects that go in these research lines. So there was so far a completed bachelor project, and there are currently in progress a master and a PhD project. There is part of a PhD thesis of Vivo Sengo here that is also in this direction. And, the research line also has been, so it has been served as motivation to acquire some resources from the group, in particular an advanced computing project of 20 million CPU hours at Mare Nostrum that was used by some members of the group. So, what comes in the future? So, in this case, I will. So, of course, there are many things that are coming in the future. So, Pedro already mentioned about AI. That is indeed something that will really change things a lot. But there are other potential revolutionary missions that may change a lot the way we study black holes and the black hole environment. So indeed, in the timeline that Pedro presented before, there was the plans for completing the extensions to the EHC. That is the next generation EHC that should be operational in 2030 or 2031, so the beginning of the next decade. There are plans for space-based missions. One of them is the Black Hole Explorer, but there is also another European initiative. This will bring new capabilities. For example, the possibility of doing black hole movies, a 4 times increase in resolution, and 100 times increase in dynamic range. That is the ratio between the brightest and the less bright points in an image. And potentially, they will also come with the possibility of detecting other black hole shadows that are of a much smaller size compared to the two sources that have been studied so far. And very interestingly, also they come with the possibility of studying some other objects that are claimed to be binary black holes. So this will really open a very large window of possibilities for us theoreticians to study. And well, of course, this will also come with opportunities to find new fundamental physics in a completely unexplored environment. So, and well, I hope that we will join as well in this new adventure. So thank you very much.
Thank you very much, Héctor, and we hope that we can explore these new opportunities with you. Thank you. So